Thanks everyone for coming to the talk, and I wish I could be here with you, but yeah, to different reasons I couldn't make it. So I'll be telling you about parity games, essentially, which is as I will kind of explain and highlight, is a subcase of mean payoff games. And the question that we were looking at for some time is, can we extend the recent progress that has been made on parity games to mean payoff games? And so somehow this is a report on our understanding on that question. All right, so just to get on to be on the same page, so those are mean payoff games for me. So those will be the deterministic versions. So I don't have any stochastic aspect here. So on the right, you see a mean payoff game. So I have two types of vertices, squares and circles. You just need to remember that squares are minimizers and circles are maximizers. In the context of mean payoff game, it makes a lot of sense to call them min and max. For parity games, I like to call them even Adam, but that's not going to matter so much. So on every edge, we have some weights, and then as usual, we do the infimum limit of average of prefixes. All right. So maybe the first and key property to these games is positional determinancy, which exactly says that both players, both minimizer and maximizer, have optimal memorialist strategies. And so here is an example of that fact. So on this game, I may have messed it up, but hopefully it's correct. In blue, so you can see here in red, and here in blue, two optimal strategies. And so basically what this is saying is that optimal strategies are essentially just choosing a cycle in the game, right? I mean, when both players have chosen their optimal memorial strategy, meaning just one edge from every vertex, then essentially what we're done with is just some cycle. And I've read somewhere, I actually don't remember where, but this expression games of cycles. And I think this is something useful to keep in mind for what's going on later. Essentially, mean payoff games, as parity games will be just in a second, are games of cycles, and this will be instrumental to the techniques that I will talk about today. All right. So now I want to talk about parity games. So syntactically, it's really exactly the same. I have circles and squares. Just for reminder, circles are for Eve, squares are for Adam. And now instead of weights, I have priorities. So priorities are natural numbers in 1 to d is some parameter. And now the condition is the following one here. It's a mouthful. It says that Eve wins an infinite sequence of priorities if, when we look at the maximum priority that appears infinitely many times, this priority is even, right? And so that means that if the maximal priority appearing infinitely often is odd, then the other player is winning. This is still a zero-sum game. So the first point I want to make, just to kind of clarify and connect this to mean payoff games, is that this is really just a special case of mean payoff games. So what I've done here is I showed you a parity game, the one from before that you can see in red. And I just replaced in this blue-greenish the priorities with weights, making it a mean payoff game that's equivalent as a game. So what's the idea? Here we have 4 vertices, right, in this game. And so that means that if I'm using powers of -4, right, in any cycle, the weight that will dominate in a mean payoff calculation for a cycle, the weight that will dominate is the one having the highest priority. In other words, when I now look at what's happening as a mean payoff game, when both players play optimally, when I look at a cycle, I don't actually need to produce the sum of all the values. I just need to look at the maximal one, the one having the maximal power that's here, which is exactly the priorities that I have extracted. And this will tell me whether this cycle is positive or negative. So in that sense, deciding parity games is the same as deciding mean payoff games for the threshold 0. If it's positive, then Eve wins. If it's negative, then Adam wins. So that's how parity games are a subcase of mean payoff games. This is a well-known thing, but I wanted to just highlight it to be on the same page. All right, so the beginning of this story is in 2017. There's a fantastic paper by Kalude et al., which brought the complexity of solving parity games down from mildly sub-exponential to quasi-polynomial. So what does it mean? What was exactly the complexity? It's often reported as this complexity, which is n to the power of log d. So n here is the number of vertices in the game, and d is the number of priorities. What we had here for labeling the edges, right? So this is not polynomial because log of d is not a constant. This is called quasi-polynomial because it's, well, yeah, almost polynomial. I think it's actually a bit more insightful to look at this complexity like so. So the actual kind of non-polynomial term actually looks like this. It's a binomial coefficient of log n choose d plus log n. And then you can sort of analyze this binomial coefficient and it gives you the blue upper bound here. But I would like to argue, and we'll see a bit later, that actually this yellow term is kind of the most significant here. All right, so the question is, what about mean payoff games, right? So there's this beautiful idea for parity games. And as I will come back to it in a second, there are actually many quasi-polynomial time algorithms for parity games. There are, I don't know, maybe 4, 5, or 6 at the moment. So can any of these be extended to mean payoff games? Or can we gain some insight about mean payoff games from this special case of parity games? So, well, the answer, the short answer is no. And the long answer is a bit more complicated. We learned something on the way, but somehow that did not get us to much better algorithm for mean payoff games. So this is a bit of a long story, and unfortunately, I will not have time to kind of go through all these 4 steps, but I will discuss in a bit more detail the second step, which I think is crucial here. The first one is saying that in all the existing algorithms, there's kind of some underlying combinatorial fact or combinatorial idea that seems to, pervade in all of these, and this is this so-called universal trees. Now, the second thing is universal trees have exactly quasi-polynomial size, and actually this quasi-polynomial size is exactly this value here, right? So they have quasi-polynomial size, and by this I mean both upper and lower bounds. So we have constructions of universal trees of that size, and we can show that we cannot do any better. All right, so all of this here is really about parity games. Now the question is, do we have some tool? Can we extract some tool from this that would extend to mean payoff games? And so that's point number 3. Universal trees are for parity games. Now you can extend this to universal graphs, which really will be, as we'll see, exactly the same notion, but just generalized from parity to either you can see it for mean payoff games or more generally for any conditions that's positionally determined. So as we've seen earlier. Another bad news is, if you look at universal graphs and what algorithms you can get from them, then this is the best complexity we can get in some provable way. And that's essentially the state of the art. I mean, that was the state of the art before all of this. So we just made a small improvement that's here. What was known was actually O of n, n, and we brought it down by a tiny ridiculous exponent, which really makes no difference, or very little difference in any implementation of that. All right, so now I will just kind of try to give you some ideas about all these 4 points. I mean, not all of them. I will mostly talk about the first one and the third one, how to extend this tool to mean payoff games. And by the way, this the next talk is actually just exactly. I mean, this is a very good introduction to next talk, because next talk will see how universal trees can be used actually for yet another way of attacking this parity games question. So universal trees, this is this. So first of all, I need to define what kind of trees I'm interested in. So the trees, this is here an example of a tree. I just have 2 parameters, so 9 and 2 here. 9 is the number of leaves, so the size of a tree will just be the number of leaves it has. And 2 is the height. So here I have just depth or height 2. And just to make it clear, when I have a node, and those are the 3 children of this node, then they are totally ordered. So the way I'm drawing them really means that there's the leftmost, the second one, and then the third one. So my trees have fixed height, a certain number of leaves, and every set of children is totally ordered. So now this is the definition of a universal tree. A tree T is NH universal if for any NH tree, so any tree with n leaves and height h, this small tree T embeds into T. So it's universal in the sense that it just contains, in a sense that I will illustrate in a moment, contains all trees for parameters n and h. So this is an example of a tree that's 5-2 universal. So it means that whatever 5-2 tree I can draw, so let's look at, maybe this is a 5-2 tree. I have 5 leaves and it has height 2. I'm saying that this guy embeds here. And, the reason is simply, for instance, I have this thing here, then I can have a 3 leg here, and for instance, that one here, right? And if you just repeat this for any of the 27 trees that exist, 27 5-2 trees, then you will see that you can embed it in this 5-2 tree, and actually it's actually minimal. This is a minimal 5-2 universal tree. All right. So now the question is, how does this relate? How does it help for parity games? And what do we do with it? So I like to call this result the fundamental theorem. I don't think anyone else ever used that word for this, but I think it's fundamental in the sense that this is basically the one reason why we're interested in universal trees for parity games. And this is a key property that's used in correctness proofs of all algorithms I know using universal trees. So it should look rather familiar to you if you think about it as a value iteration question. So let's take a parity game. And now what I'm looking for is a structured witness that Eve is winning in this game. Right? And so this fundamental theorem is just an equivalence result that says you win if and only if there exists a tree. So you can find some tree. This tree is a n d-half tree. So just a quick reminder, this is the number of vertices, and this is the number of priorities. such that this tree embeds into your game. And so in some sense, this tree is both a representation of your winning strategy and a certificate that this strategy is indeed winning. Right, so let's just do a quick example to see what it is. So I'm taking this very simple game on the left hand side. Sorry. So this is a parity game where Eve wins. So she just has one vertex where she can choose. She can either go up to V, or she could go down to W. And well, basically here she wins by just playing this thing here, because either we'll have a loop VW, which is 4 and 3, so the maximum priority is 4, or we follow kind of this big loop here, and then we have 1, 4, and 2. And the thing is, a witness that she wins will be given by this tree here. And how so? So now I'm giving you the embedding. So this is here, the embedding. I represented my tree here. And I'm saying I map U to this leaf, W to this leaf, and V to this one. And this satisfies a bunch of properties that are here. These properties are looking at the tree. And the point is that trees are defining sort of a set of orders. So those are the orders, 1, 2, 3, and 4. And now if I look at all the edges in this game, then I can see that they satisfy all of these properties. The properties are just saying, I am to the left of this. So for instance, I have this edge from U to V, and it's labeled with priority 1. So that means that I have to have that U is put to the left of V if I look at order number 1. And indeed, this is the case. U is in the left of V in this embedding. And so I will say so on and so forth. I check that all these properties indeed hold here. And just by checking this property, that tells me that not only this is a strategy, but it's actually winning, meaning it's enforcing that all the cycles are even. All right. And now there are many kind of different ways of using this fundamental theorem. So the original one by Kalude et al. Was somehow, let's call it automata-based. In some sense, it was building some sort of automaton that relates to universal trees in some non-explicit way. The maybe most natural one for this crowd would be value iteration approach, which operates directly on the universal tree. Another one that came later is recursive attractor decompositions that sort of mimic existing algorithms for parity games by also doing sort of some induction on the universal tree. Now the next talk will be a strategy iteration. So this is just Cedric's talk just next. So I will not talk about this much, but this is kind of to show you how this fundamental theorem can be sort of used in different ways to construct algorithms. All right, so now I'm moving on to how do we go from parity games and universal trees to mean payoff games? And the answer is, or at least one answer that we're giving is this notion of universal graphs. So now what I'm describing here is I just define universal graph in such a way that the fundamental theorem holds for them. So the definition of universal graphs is just those are the graphs for which the fundamental theorem holds for mean payoff games. So I'm saying I take a mean payoff game. So let me just give some parameters. I have n vertices, and let's say my weights are natural numbers or integers between minus n and n. Now I say U, a graph, is n universal if winning in your game is just equivalent to there exists a morphism, or what I called earlier an embedding from the game to the universal graph. And that means that as soon as I gave this definition, then I can sort of extend everything that we knew before. And the best thing you can do is the following. So if you have a universal graph, if you manage to somehow construct a universal graph, then that gives you, in a generic fashion, an algorithm for solving mean payoff games in complexity that's this. So again, the number of vertices times the size. Number of vertices in U, which means that the question, so here this is number of vertices in G. So that means that the question now is really, can we construct small universal graphs? And so this is how the answer is not really. The theorem, so our main technical result there is saying there exists an NN universal graph, and the size of which is this number, so it's slightly smaller than n to the n. And unfortunately, we essentially, we essentially cannot do much better.
Nathaniel?
Yes.
Could you remind what the morphism was? Just because, how does it match with the weights, I guess? Is there any, I kind of missed that with the Parity Games as well.
Yeah, that's because I didn't want to tell you in full detail. So let me tell you a bit more. So let's get back to this place here. The thing is that it's a bit of a lie to call it a morphism, because what I'm actually mapping are games. And that means that I have to take care of two types of vertices, the circles and the squares. So if I want to map, okay, let me write here. What I will want to do, if I were looking at just a graph, G, then a morphism would just be a function phi, let's say, that goes to one graph to another graph, such that if I have V with some weight W to V prime in G, then for the same weight, I will have this in G prime. Right? So this is, I would say, the classical notion of a morphism for graph structures. Right? Now things are slightly more complicated. Let me push this a bit down because I'm talking about G, a game. So I have to deal with two types of vertices. So again, what I would call a morphism is still from this to that. But now I will say if V belongs to Eve, then I want to say there exists V W V prime in G and phi of V W phi of V prime in G prime. The reason is that I'm just looking for a winning strategy, right? So I don't care for all the edges coming out of the first player. However, if I'm looking at the other player, then it's adversarial. So here I will just put for all. And the same thing here. Okay, that's a bit of a mess, but you got the... Right, so let's say graph morphism is the classical notion. For games, it will be just slightly adapted to fit the two types of players. And here, I was hiding it a bit. Oh, sorry, where is that? Yeah, in this example, I was just hiding it a bit. indeed, we need to check this morphism property only for one edge of U, which is the one that she chooses in her winning strategy. And then we need to check it for all vertices of Adam, because we want to be universal for whatever actions of the other player.
So
it makes sense?
Yeah, so just to be clear, in the universal graph or tree, the graph or tree itself doesn't have to distinguish inside itself what is coming from one player and what's coming from the other. That's only in the quantification. Like
exactly.
Okay.
Yeah. So this is the kind of nice thing, is that you're mapping into a graph, and that graph doesn't have any knowledge about who's playing or anything. The mapping itself is taking care of the interact or who's playing. Right. So this is at the level of I lost it. I don't know where it is anymore. Yeah. So this is at the level of the morphism, that we care about who's playing.
And could you just say one word about the relevance of the d over 2?
Yeah, that's a good question. So that actually a very good question, and that I can fix a typo here. And that's actually an important one. This should be d half. And this is important. Actually, it makes a whole difference. I mean, it's slightly smaller, obviously, but that's not the whole difference. The reason for d half is that those algorithms are intrinsically asymmetric. So what I'm doing here, when we look at this fundamental theorem here, I'm solving the game by looking for a witness for Eve, right? And therefore, this d half is actually only recording progress for the even priorities. And somehow the odd priorities are used in taken care of in a different way. And so this fundamental theorem is very much asymmetric in the sense that we're really only talking about the point of view of Eve. For that reason, we can only have half of the priorities. Now, some of the quasi-polynomial time algorithms that sort of restore this symmetry will have the disadvantage that they will actually here put a D. So this attractor-based algorithm, which is really a very symmetric approach using universal trees, will replace D half by D. And that's because you need to consider all priorities. Whereas naturally, these universal trees and the way they're used in this fundamental theorem is very much asymmetric. So I said what I wanted to say. So thanks for this very good questions that triggered some interesting remarks.
Right. Yeah. So then, thank you.